entanglement island. Please start.
Hi. I would like to thanks for this invitation, and also thanks organizer for this annual wonderful meeting. And I hope this annual meeting go on and every year. And today I will discuss about the entanglement island and the Janus black hole. The reason why I put the parenthesis in the Janus black hole is that maybe I would not have enough time to explain everything. So in my in this talk I aim that I just give the introduction to the entanglement island and some introduction to our work with our work. And this talk is based on the this paper collaborated with Dong-Soo Park and Cham-Ju Kim and Sang-Eun Lee. And I have to apologize in advance if I make a certain hiccup, because I suffer from the hiccup from last night, but it still keep going. So sorry if I make a hiccup. So let's begin with one very simple question. We can ask, what is the state of the black hole? So, which means that you can consider the density matrix of black hole, and you can ask whether it's pure or thermal. So to answer this question, we already know that black hole is like a thermal object. This can be easily seen in the Bekenstein-Hawking entropy, which is proportional to the area of the horizon. Also, black hole follow the first law of thermodynamics, where this mass is analogous to the energy, and kappa, which is the surface gravity, is correspond to the temperature of black hole, and this entropy corresponds to the area of the horizon. So from this point of view, black hole, you can say that black hole is in mixed state or thermal state. But let's try some Gedanken experiment or thought experiments for the black hole formation and the evaporation. For simplicity, I will take a very simple assumptions. First, before black hole is formed, I consider some initial state of the matters are in the pure state. Also, I assume the unitary evolution as time passes. In this situation, before black hole is formed, of course, the state is pure mass. There are a lot of mass, and I consider some small universe. And after a black hole is just formed, and let's say every matter is collapsed to the one black hole, then you can say that black hole is also maybe in the pure state. And then as time passes, there will be Hawking radiation, and let's say black hole is evaporated completely. Then there is no black hole, only some radiation in the whole space. So in this case, you can ask, what is the final state after the black hole evaporation? This is also, you can, whatever the intermediate step, because we assume that the initial state is pure and we assume the unitary evolution, the final state should be pure. So if you believe if you assume the unitarity, so this is, so in this case, the final state is pure. So it seems that there is some a little bit discrepancy. So when just the black hole is formed, it looks like in the pure state. But this is contradicted to the previous slide, where the black hole is a thermal object. Then what happened? So this seemingly contradiction can be explained by the fact that the pure density matrix is very close to the thermal density matrix. So which means that it's very difficult to distinguish the density matrix of pure state and the thermal state. For example, the pure state and the difference between the pure state and the thermal state, which is the Boltzmann weight, is exponentially suppressed by entropy of the black hole. Actually, this happens in many systems in the very complicated system, like chaotic system. This is very also thermalized system, like the ETH, eigenstate thermalization hypothesis is also in the very similar to this situation. So, up to this small correction, this pure state is more like behavior like a thermal state. So at early time, you can drop this, you can ignore this small exponential suppressed term, and then you can consider you can perform the semi-classical perturbative calculation, and then it just gives this thermal result, like a Hawking calculation. However, after a long time, then one cannot ignore this small term anymore, because very long time this non-perturbative effect would play role. So in this case, one needs to distinguish this pure state and the density thermal state. So let's consider this page curve. So we still assume that unitary evolution, and we also consider some closed quantum system. This is also somewhat would require. So let's consider a very simple system where the universe is made of the black hole, which is just formed, and some thermal bath. And when there is no Hawking radiation, and let's say black hole is in pure state, then the entanglement entropy between the black hole and the bath would be, or radiation, is zero, because there is no thermal radiation. So as time passes, the entanglement entropy of the radiation will be increased because of the Hawking radiation. Because of the Hawking radiation, there will be EPR pair will be created. So entanglement entropy will keep increasing. So this is nothing but the Hawking calculation. And if you keep this semi-classical calculation and there will be no decrease of entropy. So at the final stage, when the black hole is evaporated completely, the entanglement entropy would not be zero. So you can say final state is mixed. And also, there is a chance that if you don't consider like closed system, then it's possible to make some baby universe. So even though black hole is completely evaporated, there could be some entanglement between the space and some new universe. But however, we assume the unitarity and the closed system. Then whatever the intermediate state, the final state where there is no black hole should be in pure state. So in pure state, the entanglement entropy should be zero. So at some point, the entanglement entropy should start to decrease. So this time we call the page time. So this is a type of is some short story of the summary of the black hole information paradox. So there were many proposals to resolve the information paradox. Actually, black hole, this is the previous page curve is one of the famous information paradox, but actually there are many types of the information paradox which attack which attack certain aspects of the black hole information problem. So there are a lot of paradox, and accordingly, there are a lot of resolution to resolve each paradox. One of the famous paradox is strong sub-additivity paradox. This is not the talk for this SSA. So in a word, this paradox means is related to the monogamy of the entanglement entropy. So, and to resolve this paradox, this AMPS, which is Elmhirey, Marloff, and Polchinski-Sully, propose a firewall. The purpose of this firewall is break this entanglement between these Hawking pairs, so that it resolves some strong subadditive paradox. Yeah, so this firewall break this entanglement entropy by hand. So if we have firewall, there is no the theory is not unitary anymore. Also, there is other proposal for the first ball. This is in a word, or this proposal is that when observer is far from the horizon, it still looks like the black hole looks like a classical geometry. However, if you close to the observer, approach the horizon, now the horizon is not the usual classical geometry anymore, but the observer could see some quantum state instead of this horizon. They will see some football of strings, and there is no inside of the horizon geometry. So many black hole paradox is related to some Duncan experiment inside of the horizon. So, but this first ball does not have any inside, so it's immediately it resolves many paradox. Also, it does not have a singularity, so it looks very nice, but still, this is I'm not sure the status of this first ball, but so there is one kind of some proposal. And the last three. The most interesting and important resolution in this talk is black hole complementary. So black hole, in fact, there are several versions of black hole complementary. So the first one is proposed by Susskind and Sorasius. So simply speaking, this means that the description by impelling observer jumping into the horizon need not to be same as a description by a observer outside, stationary observer outside of the horizon. So this, but after that, many people developed their own black hole complementary definition, and one of the interesting definition is that the black hole complementary means that the degree of freedom inside of a horizon, or you can say bulk field inside of horizon, is not actually it's not independent of degree of freedom out of the outside of horizon. So schematically speaking, the bulk field inside of horizon is actually a very complicated function of bulk field outside of the horizon. Of course, this cannot be a simple function, but the number of field in this function would be like exponentially large of the e to the s number of the field. Actually, this was actually studied in math literature, and in the math literature, this is called modular automorphism. That means that the relation between these two fields is modular automorphism, and the discuss is very well developed by Tomita Takesaki theory. In physics, you cannot use this theory directly, but you need one more ingredient: the separation of a simple operator from the complicated operator. Actually, this is very important in the ADHFT. When you do the ADHFT, you only consider the simple operator, because if you introduce some very complicated operator in your calculation, it immediately changes the background. Of course, you can do that, but then you have to change the background, and this is not the effective field theory would be changing. So when we do this perturbability calculation, we usually consider the simple operator. And this within this effective field theory, then this simple operator and the complicated operator. When I say complicated operator, I mean this bulk field inside. So bulk field inside of horizon is very complicated operator of the outside bulk field. And within the effective field theory, they are independent. If this is the case, you can immediately you want to ask a lot of questions because now locality and the causality is very non-trivial. And if this relation make it might break this causality. So, but there is a lot of development and discussion by Subrat and Raju and Papadodimas, it's really consistent with holography. So they put state dependent and this, in my opinion, this state or this this version of complementary is very important in the island conjecture because here you separate this inside degree freedom of the outside and inside. You separate this degree freedom inside and outside and treat them as independent. But the island story is, in short, the breakdown of this separation. So now we will focus on the after page time. Because early time, we know that the semi-classical calculation is enough to reproduce this increase of the entanglement. However, in order to explain the decrease of the entanglement entropy after page time, I mentioned that we need to distinguish this pure state and the thermal state, or we have to now take care of this non-perturbative correction. In this case, you would require this quantum gravity, and for every you have to capture the non-perturbative effect very precisely. But as you know, this quantum gravity and the non-perturbative calculation in the gravity is very, very difficult. So it should be very precise. So for now, we don't have enough technique. Of course, in the supersymmetry, if you have supersymmetry and zero temperature, you can do some non-perturbative calculation. But this is not the zero temperature, or this discussion need not some supersymmetry also. So because of that, until recently, people say there is no way to calculate this decrease of the.
Okay. I have a question. You wrote down the pure state density operator and 1 over Z. So usually the trace of density operator should be 1. So this Z is a partition function for thermal state or partition function for all, including
thermal state. This is really indeed the thermal state.
This means that the trace of the other part should vanish, right?
Yeah, so there is some discussion. So you mean this like a trace row should be 1, and this should be also 1, but this will be vanishing. Yes, so in this case, so one have to find what this means. In nowadays, people trying to explain this by random metrics. So this is some matrix R. So average of the matrix R is vanishing. So this is one proposal.
Of diagonal component?
Yes.
Okay, thank you.
I mean yeah. So this here, I also trying to using some averaging. So you know that the average of the random matrix is 0. But if you don't average it, it's hard to say. But anyway, there is some other discussion recently, so it's also very important. Yeah, thank you for a good question.
Thank you very much.
And so there is no way for now. People expect that. Also, you also would agree that so far there is no way to calculate the decrease of entanglement entropy using the semi-classical calculation. This is important after phase time. However, always a prediction is often made in order to be disproved in future. So this expectation, this island conjecture, one of the in my opinion, one of the big progress of this island conjecture is that they allow us to calculate the decrease of the entanglement entropy semi-classically. This is one very important achievement nowadays. So to explain that, let's already generalize the entropy. So we know that this Bekenstein-Hawking entropy, which is proportional to the area of the horizon. So when black hole is evaporated, then the area of the black hole will be decreased. Then it seems that the entropy is decreased. So then this sounds like this like the second law of thermodynamics. However, this second law is valid only the closed system, not the open system. So in order to explain the second law, we need consider some closed system, which is we have to include not only black hole, but also this radiation and the matter outside of the black hole. So for this, we define generalized entropy, which include the black hole entropy of the black hole, as well as entropy coming from the radiation and some other matter. And we can also already generalize this. We can consider some more other, like a generalization of this generalized entropy by using this other co-dimension 2 surface, which means that when we talk about this black hole entropy, we consider this, we choose this horizon as a co-dimension 2 surface. But if you consider the Ryuta-Kaneki surface, you consider some arbitrary co-dimension 2 surface. Then we can define generalized entropy depend on this co-dimension 2 surface by this area of the co-dimension 2 surface plus the co-dimension 1 surface outside of this X. And then we calculate this entropy of the matter or radiation in this sigma X. Also, this calculation, when I calculate this entropy, I calculate the semi-classically, which means that background is fixed. Otherwise, this is a quantum calculation, and if background is dynamical, there is no way. Of course, there is another exception. And here, X is arbitrary. So in order to fix X, we in physics usually take extremization. So we will extremize this generalized entropy with respect to the X. Then there will be some local extrema. And there could be many local extremum. Then among the local extremum, we will choose some global minimum. Then you can easily expect that there will be some transition between the different local minimum. So that as the spoiler, this will give some page curve. So this island conjecture is actually, there are many papers, and each paper, there are two types of approaches. So here, island conjecture, the purpose of island conjecture is calculate the entanglement entropy between the black hole and the radiation. But you can calculate that entropy from the point of the black hole or from the point of the radiation. But however, the two calculations should be equivalent. If you total system, the black hole and the best, the total whole system is in the pure state, then this is a very well-known fact that the entanglement entropy should be same if the whole system is pure. So they are equivalent. So some paper using the count the black hole entropy, some people calculate the entanglement entropy from the point of the radiation, but they are equivalent. In this talk, I will explain from the point of the radiation. So here, for simplicity, I will consider this evaporating black hole. So there is a horizon and the black hole, and I put some cutoff here, so that all the black hole degree freedom is inside of this cutoff. This is roughly far from, you can say, the distance between the horizon and the cutoff is like a Schwarzschild radius around. And this is, you can say that this is kind of separation between the black hole and the bath. And then I will consider the time slice, and then in the bath, and then I calculate the entanglement entropy of this times on this time slice. And then if you calculate the entanglement entropy, then it will be increased. And this is similar to the Hawking calculation. And this is, of course, old version. However, then what is the new ingredient in this island conjecture? In this island conjecture is introduce some another time slice inside the horizon, so that when we calculate the entanglement entropy of radiation, we consider the entanglement entropy of the not only radiation on this sigma radiation, as well as this sigma x. So, and also there will be some co-dimensional two surface stay here, so that we also include this contribution of this entanglement entropy of this surface x. And then we will, as before, we will extremize this generalized entropy with respect to x, and we choose global minimum. And this island conjecture proposed that this quantity, this is a quantum extremal surface. It gives the correct entanglement entropy of the radiation. And usually, when you extremize this some quantity, usually there is two types of the extrema. One is the extreme happen in somewhere here, and the other extreme usually happen at the boundary here, at the boundary, which means that this area of the x just vanish. So we have two local extrema. So this is a vanishing island, and here there is non-vanishing island. So vanishing island, as before, the entanglement entropy will increase. Non-vanishing, however, non-vanishing island, the entanglement entropy is decreased as time passes. This requires some detailed explanation, but in a short, the essence of this mechanism is that if you calculate the entanglement entropy of radiation, we count the EPR pair of this radiation. But when we include this island, both this pair of the EPR pair, which come from is related to the Hawking radiation, is included the sigma x and the sigma radiation. So it does not contribute to the entanglement entropy anymore. So in a short, In a word, I can say that this island purified the EPR pair of Hawking radiation. So in this mechanism, the island, when you include the island, this decreases the entanglement entropy. And more detail, you can see this paper. This part is a little bit similar. It's based on the Margasena paper. And then this non-bench island contribution will be decreased. So that if you choose the local global minimum, there will be transition between the two local minimum, and this is exactly give the phase curve. So I already have a 30-minute, but can I already continue, keep going? Maybe, yeah, okay. So so far, this is a very qualitative calculation. You can ask where is a quantitative one. So when you say we calculate the semi-classical, that means that there must be some quantitative calculation. So people, usually it's very difficult, but the people, to calculate such entanglement entropy, you have to go to the very simple model. So there is low dimensional model was possible. So here you consider some quantum mechanics coupled to the CFD2, and the quantum mechanics you can expect some very hot system, and the CFD2 is very cold, like you can expect some thermal bath. And then you know that some certain very chaotic quantum mechanics can be dual to the 2D black hole. So that using the holographic dual of this quantum mechanics, you can, this model is dual to the this 2D black hole coupled to the CFD2. So that this situation is more like a 2D version of this island story. So these people calculate the entanglement entropy and show that this is page curve. However, you can go to the higher dimension. So this is called doubly holographic picture because CFD2 is dual to the ADS3, and the ADS2 or this 2D black hole can be considered as some brain in the ADS3. So of course, this is kind of conjecture. No one proved it, but certainly there is a very good advantage of that. So usually in the calculation of entanglement entropy is almost impossible. But in 2D conformal field theory, you can calculate it by using conformal symmetry. So 2D is very special. However, this is still very difficult quantum calculation. Of course, it's possible, but very complicated. 2D is still simple, but however, in the higher D, the advantage of the ADSFT is that quantum calculation in the field theory can be reproduced by semi-classical calculation in the gravity, in the higher dimensional gravity. So if there exists this doubly holographic model, this entanglement entropy is nothing but the Ryutakane surface in the ADS3. So with Dongsbach and Chan Joo-kim and Sang-Eun Lee, we consider the Janus black hole in 3D and calculate the entanglement entropy and trying to find the relation to the island. Probably here there are many experts on the black hole, and I will not explain the detail, but this you can consider it as some kind of deformed black hole in 3D. And the important thing is that this Janus black hole is due to the interface CFT, which means that you have CFT and there is some interface degree freedom live in the x equals 0. So we know that here previously that the previous approaches is bottom-up approaches, but here we have concrete ADS3 black hole. So then you can consider like a top-down approach. So this three-dimensional picture is well defined. And of course, this lower dimension, this interface CFT is also well defined. And our proposal is to find some 2D description of this interface degree of freedom. So this is motivation of this paper. And the entanglement entropy, as you know, it's very easy to calculate in the ADS3. And we consider this two-sided Young's black hole. So we have a shift I shifted right and the I shifted left, and I consider these two intervals. So as you know, there would be two types of the Mutakanai surface, which connect this left and right, or this disconnected Mutakanai surface. And there will be some phase transition between them, and this corresponds to the page curve. So as you know, usually there is some transition between this Mutakanai surface and this gives some transition in the entanglement entropy, and you can say that this is a page curve of the eternal black hole. Previously, it's the page curve of the evaporating black hole, but the eternal black hole case, the entanglement entropy did not go to zero, but it saturates the thermodynamic entropy. So here we found a very interesting behavior. So here this is page time, and after page time there is a constant. It's saturated, but if we consider some limit where the influence of the interface degree of freedom is stronger, then there you can find some time window where the slope of the entanglement entropy is changed. So early time it's C/3, as this is usual behavior, but this when interface degree of freedom becomes stronger, which means that this interval is approaches the interface, or interface degree of freedom very stronger, then it starts to behave in this way, another slope. And then this, we found this is late to some shadow region touch this Mutakanai surface. So far, now it's time up, and there is still many open questions. So we're trying to find this 2D description and have some certain evidence, but this detailed 2D description, 2D gravity description of the Janus black hole is not that clear. So this is still open problem. And here, some of you might say that this island conjecture is just a prescription added by hand to reproduce the correct page curve. But of course, this may be by chance, but if this is really fundamental phenomena, you have to ask what is the origin of the island. And this is very important open question. And so far, we just reproduced the page curve, but we never talk about what is density matrix of the black hole after page time. So to find the state is also very important open question. And you can also ask what is the higher dimensional generalization, like for example, super Yang due to the 5D black hole. So in this higher dimension, it's almost impossible to calculate the entanglement entropy as usual. Just quantum calculation would be very impossible. But if there exists some doubly holographic picture, maybe then in the one more higher dimension, there may be some way to calculate the entanglement entropy using the Mutakanai surface, and it maybe reproduce the page curve. So this would be very interesting direction, and thank you for this listen to my talk.
Okay, thank you very much. Is there any questions or comments?
Excuse me. I have a question. So,
okay.
So your computation is, I think your computation is generalization of Hartmann and Maldaceni's computation. Is it?
You mean this Maldacen Hartmann is kind of there is many papers by Maldacen Hartmann. This is a review paper.
No. they computed the time evolution of entanglement entropy as
Mhm. You mean this paper?
no. So you computed the time evolution of entanglement
Mhm.
entropy
Okay.
of
I mean, okay, or there is a Baldassare-Hartmann paper is maybe other paper is some replica wormhole. That is a slightly different approach, but anyway, you mean this one, probably, you mean this one,
no. So
calculation of this,
2013
or this one?
paper.
I see. Yes.
And
I
I
see,
think
yes,
in
okay.
their paper, they computed the time evolution of entanglement entropy by
Yeah.
field theory side and holographic side.
Yes.
Then
Yeah,
in
this is
your
exactly
case,
this story.
yes, then in your case, can you compute the time evolution from field theory side?
Yeah, so yes, of course, we also did. This is just simply using the 2D Shapley calculation, but we have the interface degree freedom. So the where top down? Yes. The entanglement entropy calculation. This is a very classical calculation. It's easy, and here you can also using the conformal symmetry, and it's also I would say it's easy. Not that easy compared to the classical, but it's possible. So we already did, yes. Even though we didn't give a present in this talk, but yes.
So you check the correspondence between field theory computation and holographic computation.
Yes.
Okay. Thank you.
Yeah, the difficulty is like a 2D description, and from in this picture, how to calculate it. And then,
Thank you.
okay.
Okay, anyway, time is up. So let's thank speaker first, and then, yeah, you can discuss freely until 2 p.m. because it's a lunch time. So afternoon session will start from 2 p.m. And anyone who have question to Junggi, and yeah, keep discussing.
윤정기 박사님. 윤정기,
안녕하세요. 네.
예. 그 저기 원래